What is a matrix? Let us see with an example. Suppose there is a furniture factory which manufactures chairs, tables and carts. These furniture require certain resources. Each of these furniture require certain amount of wood, let us say 100 units, labor 200 and paint 300 units. Likewise, a table also needs wood, labor and paint 150, 200 and 250. A cart also needs 200, 250, 300. When these furniture and their resources are arranged in rows and columns, this form is called matrix representation. A matrix by definition is arrangement of numbers, or also known as elements, arranged in certain number of rows and columns. Now let us review some of the basic concepts in matrices which we have learned in our high school and junior college. The first one is addition of matrices, then multiplication of matrices, transpose of a matrix and inverse of a matrix. If we want to add two matrices A and B, what we have to do is simply add corresponding elements in both matrices to obtain the third matrix. A ij plus B ij equal to C ij. 2 plus 3 is 5, 1 plus 7 gives 8 and so on. Just simply add the corresponding elements. So in order for the matrix addition to be possible, the both matrices must be similar. That means they must have same number of rows and columns. Multiplication of two matrices. In order to multiply two matrices A and B, the number of rows in the first matrix A must be equal to number of columns in the second matrix B. We have to obtain the dot products of rows and columns. For the first row, obtain the dot product with the first column to obtain the first element. 1 multiplied by 9 plus 2 multiplied by 8 plus 3 multiplied by 7. The sum of these give the first element in the resulting matrix, and so on. Transpose of a matrix. The transpose of a matrix A is a matrix, new matrix obtained by interchanging the rows and columns of the original matrix A. For example, here the rows 1, 2, 3 become the column 1, 2, 3. Row 4, 5, 6 elements become the column elements. Third row elements become third column elements. This is denoted by AT with a superscript T on the original matrix. The inverse of a matrix. The inverse of a matrix is another matrix which, when multiplied by the original matrix, gives the identity matrix. So in order for a matrix to have an inverse, it must be a square matrix. Not all square matrices have inverse. A square matrix without an inverse is called a singular matrix. For example, let us see this matrix here. 4, 3, 3, 2 is the original matrix, and minus 2, 3, 3 minus 4 is the inverse matrix. When you multiply these two matrices, what we get is an identity matrix. A real matrix is a matrix whose elements consist of entirely of real numbers. They do not contain any imaginary or complex numbers. All elements are real. A square matrix is said to be symmetric for its all elements Aij equal to Aj. That means for the first row, second column must be equal to second row, first column, and so on. Or in other words, the matrix is equal to its transpose. A matrix A is said to be skew symmetric if for its all elements Aij equal to negative of Aj, or in other words, first row second column element must be a negative of second row first column, and so on. Or in other words, its transpose is equal to itself. For a skew symmetric matrix, all the elements, diagonal elements, must be 0. Orthogonal matrix. Orthogonal matrix is a square matrix with all real entities whose transpose when multiplied by the matrix yields to an identity matrix, or the transpose of the matrix when multiplied by the matrix is equal to the identity matrix, or in other words its transpose is equal to the inverse of a matrix. Look at this matrix. When you multiply transpose of this matrix with itself, what we get is an identity matrix 1 0 0 0 1 0 0 0 1. This is an example of a orthogonal matrix. A Hermitian matrix, also known as a self-adjoint matrix, is a square matrix with complex entities which is equal to its conjugate transpose, or in other words, for each element Aij equal to element Aj. For in an Hermitian matrix, all the diagonal elements must be real numbers. They cannot be complex or imaginary. Remember the symmetric matrix we have learned earlier? A Hermitian matrix is a complex extension of a symmetric matrix. A square matrix with complex entities is said to be skew Hermitian or anti-Hermitian if its conjugate transpose is equal to its negative. A skew Hermitian matrix is a complex version of a real skew symmetric matrix. A unitary matrix is a complex square matrix whose conjugate transpose is equal to its inverse. The real analog of a unitary matrix is a orthogonal matrix with real numbers. An idempotent matrix is essentially a square matrix which, when multiplied by itself, gives itself, or in other words, the square of the matrix is equal to matrix itself. The matrix given here is an example of idempotent matrix. This matrix, when multiplied by itself, yields to itself.